My dear students, I welcome all of you for today's session on system modeling and simulation. In this session, we will have a discussion about stochastic nature of output data. The term stochastic means involvement of randomness, means random nature. I mean to say the output, what is going to be generated by a model is a random. Got it? So let me review the topic we have discussed in last session. Okay. In last session, we had a discussion about output analysis of a single model. In that session, we had a discussion about the objective of output analysis. So what actually an objective of output analysis? To predict the performance of a system or to compare the performance of two or more alternative system designs. Okay, clear? I mean, let me say, there are if I call theta is a parameter that represents some performance of a system. Got it? Yeah. Then we are going to perform several number of experiments. Got it? Means for a given for the given single model, I may perform any number of experiments. Okay. The result of set of simulation experiments will be an estimator we call denoted as theta cap of theta. Got it? So in general, theta is a performance. Theta cap represents the performance that is obtained, okay, in one run. Got it? So the precision of the estimated theta cap, okay, can be measured by the standard error of theta cap. I mean, here, in general, if I run for the first time, the performance will be something. And the next, if I run a second time, the performance might be some Y. Earlier, it may be X, now it may be Y. Next time, if I run, it may be Z. Got it? The performance might vary on each run. So, but there will be some mean. Okay, I need to determine average. Okay, I may run some 100 times. Let me determine the average. Let me consider that as a precision point. Okay, so we call if I consider that mean. Okay, then each run, what the performance I'm going to get, that I'll measure in terms of standard error with respect to mean. Clear? So sometimes what I can say, rather than measuring in terms of standard error, I can specify the interval. Okay, I can specify the interval within which the performance will lie. Got it? That we call confidence interval. Got it? So in the previous session, while we had a discussion about output analysis, I told you about standard error, okay, for an estimation theta cap with respect to theta. And we had a discussion about confidence interval. What is that interval? Interval is a range within which my performance may lie. Got it? Then also we had a discussion about two issues that we need to overcome, right? While dealing with output analysis. What are those two issues we have discussed? One is autocorrelation and the other one is initial conditions. Okay, these two issues we need to overcome. Clear? So now in today's session, okay, let me discuss with the stochastic nature. Okay, I mean, I said the input to a model is always random. I mean, random number generator will make use of, and that random number generator is going to generate an input to model. Since for each run, the input to model is random, so the output what we can expect to, it's a random. Got it? Got it? So there's a randomness in the output of a model. So this is called stochastic nature. Clear? Clear with this? So now, let me tell you. First, let me have a look at agenda of today's session. Okay. So in today's session, first I'll give you introduction to stochastic nature of output data. You got it. Later, after knowing the randomness in output data, okay, in the main objective of this output analysis, what I said, to evaluate the performance. Got it. So let me take an example of a call center problem. Okay, named Abel Baker. They are the they are the executive, customer care executive. Got it. And let me take one more example, a single server queuing system. Okay. Through this example, I will tell you how to estimate the performance. Got it? Clear? Clear with this? So now, coming to first agenda, that is stochastic nature of output data. See here, see, I will run a simulation model for a specified period of time. Okay, that is nothing but starting from time 0 to an end time te. Clear? I repeat, I will run the simulation model. Not only me, everyone will run a simulation model for a specified time. That is from start time 0 to an end time te. And what is the te we had discussed in last session? Te is a particular time. Okay, that one particular time. Okay, one stop event occurs. I mean, when a particular event triggers, which stops the simulation. Okay, and what is time at that moment? I mean, the time at when stop event occurs is nothing but t. For example, in banking system, I say the start time is early morning 9:30 a.m. and the close time is what 4:30 p.m. Means in banking system, I will start the simulation at time 9:30. I will consider it as time 0, real time 9:30 a.m. But for simulation purpose, we will consider it as time 0. And the evening when clock sticks to 4:30 p.m., okay, an event is triggered because stop event means to stop the simulation. And that particular point of time, 4:30 p.m., okay, if I consider in terms of minutes, okay, totally from 9:30 to 4:30, approximately 8 hours, right? So if I 10:30, 11, 7 hours, 7 into 6, 420 minutes means TE will be 420 minutes. Clear? Got it? So I repeat, everyone will run a simulation model for a specified time from start time 0 to end time T. Got it? So one thing we need to consider, what I will call model is an input-output transformation. Model is considered to be an input-output transformation. So yeah, look at this, okay? Something and in this figure you can see that this figure represents model as an input-output transformation. Got it? So I mean here input-output transformation means I'll give some input to model. The model is going to produce some output, okay? But I'm not concerned with what output is being generated by the model. Got it? Because for the same input, we can for the same problem, I can listen to me. For same problem, I can have any number of solutions, right? So one, all the solutions are given same input. All the solutions are going to produce same output. Got it? But what I'm concerned with the efficiency of all those solutions. Got it? I mean, when I say model as an input-output transformation, here I'm concerned with, I will give some random input to model, and that output transformation here means I will, here I'm concerned with the performance of output, performance measurement of output. For example, if I say, consider this model as a banking system. Okay, consider this model. Suppose consider model to be a banking system. Okay, for example, see here, I've shown there is some random variables, right? So in first I've shown Poisson arrivals rate equals 45 per hour. Okay, this Poisson's arrival we'll discuss. Okay, arrival rate equals 45 per hour means in an hour 45 customers are going to enter to the bank. Okay, this is in one instance when I run for one time 45 customers arrive to the bank per hour. And what it says, okay, service time. Okay, so a customer may arrive for any purpose, right? For example, for withdrawing an amount from the bank, or for to deposit an amount to a bank, clear, or maybe for a loan inquiry. So his service times may vary, clear, his service times may vary. So in this case, what I have given, you can see service time below I have written n within brace d2 comma 0.2 square. So what it means I'll tell you here. So the d2 represents might be an average service time. Got it? For a customer, for example, I said in an hour 45 customers are going to arrive, right? So what may be the average service time? Okay, for each of 45 customers that represents. And okay, what is that 0.2 square means? That is a variance. I told what I said, let me consider. I said about an output analysis, I said treat as a performance parameter, treat as a performance parameter. So that is some mean service time as specified. Let me say on an average each customer will require 5 minutes. On an average, each customer may require 2 minutes for service. Got it? Now, variance, that pointer square is variance. If I find the square root of pointer square, that is 0.2, it's nothing but standard deviation. Hope everyone are clear with the mean, variance, standard deviation, right? So for example, let me say a standard deviation is 0.2. Got it? Square of standard deviation is variance. And now let me not concern with variance. I'll tell you with respect to standard deviation. Okay, what I said mean service time is 2 minutes. Now standard deviation says that 0.2 means might be for one custom. How means standard deviation is nothing but how far from the mean. Okay, how far from the mean. So for one customer, rather his service time might be 1.8 minutes. Means he got 0.2 minutes less than the mean. For the other customer, his service time might be 2.2 minutes. Means 0.2 far from the mean. Got it? So these are some input. And in this model, it says there's only one teller. Got it? Means one server. Got it? So listen, see here. Okay, given their decision variables, even among this, I said I've assumed mean service time to be 2 minutes, but in this example, mean service time is 1.1 minutes. Okay, clear? And it's a single server queue. This is about input. And what output? Every customer will come for their service, they will finish the service, and they will exit from the bank. Got it? They will exit from the bank. But I am concerned with how efficiently server is utilized. One. The other one is I'm concerned with how long each customer will wait in a queue on an average. Got it? And other measurement I'm concerned is at any particular point of time, okay, any number of persons might be in the queue. Got it? There may be any number of customers in the queue at any time. But for the entire period of simulation, starting from 9:30 a.m. to 4:30 p.m., what was the maximum queue length I've observed? What was that maximum queue length that I have observed? Got it? So this we call input-output transformation. Got it? Got it. So input-output. Yeah. For example, a customer will come for withdrawing an amount. Got it? will withdraw an amount, I will exit from the bank. The other customer will come to deposit an amount and you will exit from the bank. After depositing, you will exit from the bank. To withdraw to deposit, there will be some service time. But here I have said mean service time is 1.1 minutes. Okay, but deviation if happens, it is up to 0.2 minutes. Okay, clear? Means 1.3 minutes maximum or 0.9 minutes service time is minimum. Got it? So, but we are dealing with the performance measurement. We are output performance measurement. Telos utilization, average delay, maximum Q line. Got it? So now I said, right, simulation result is generated for a given input data. And see here, in this model, in this input, what I said, 45 per hour customer. But tomorrow there may be 50 per hour customers, right? Or day after tomorrow, there may be 25 customers per hour. Service time may also vary day to day. Clear? So, means I mean input variables to a model or random. Getting my point? Input to model or random. Got it? So, input variables to model or random. Since input are random, got it? See, the output what I'm going to get is also random. I repeat, the input variables are random variables. I mean to say, today 45 customer per hour may arrive to bank. Tomorrow 50 customer per hour may arrive to bank. Day after tomorrow 25 customers per hour may arrive to bank. So each day when I run a simulation, the input is going to vary random. Got it? So what output I can expect, even the output are random. Got it? So this randomness I call as a stochastic. Okay. So now let me tell you. See, assume just for an assumption. Okay, just for an assumption. You have designed a banking. You have designed a model for banking system. Let me consider one performance measurement. Let me call it as theta. Let me call just a theta. Theta may be okay. Just let me assume it's a. Let me assume one model is being developed. Okay, let me assume one model is being developed. Okay, the performance measurement. Let me call it's a theta in general. Okay, clear. Now today when I run that model, the performance measurement theta value found to be x. Tomorrow when I run the same simulation model with some other random input, right? Performance measurement, I got theta equals y. Day after tomorrow, I got theta equals z. So now in exam, you have asked a question: what is the performance measurement value of that particular model? What answer you're going to give? Whether you're going to answer it as x, whether you're going to answer it as y, or whether you're going to answer it as z. Because in 3 days, in 3 runs, okay, you find different answers, right? X, Y, Z. So what you're going to answer in exam? You're going to say X or Y or Z. So what we need to do, we need to determine a mean of X, Y, and Z. Got it? We need to determine a mean of X, Y, Z. Okay. And what you can say, let mean be something, okay, mean, you have a mean. Got it? So you need to tell the performance might be X with some error, standard error. That error is lies between mean and X. If other guys say, sir, answer is Y with an error between Y. Okay, the difference you need to tell. Y difference between Y and mean is an error. And the third person can answer, sir, it is Z, but with an error, and error is difference between the mean and Z. Clear? Okay. In other case, what I can say, I can determine a interval. See, I have run that simulation for 10 times. Got it? So in each of the 10 times, the performance measurement theta value is different. I need to determine the minimum value and maximum value. And what you can answer in exam, sir, the performance measurement will be between this lower bound and upper bound, and I call this as confidence interval. Yeah, got it. Now, well, let me explain you this standard error. Got it? And confidence interval through some example problem. Okay. That first problem is a call center problem where two customer executive will be there named Abel and Baker. Got it? Then the next example is a single server queuing system. Got it? So now coming to first example, Abel Baker. Okay. So Abel Baker means assume if you have any issue in your network, I mean your outgoing call, when you call to some of your friend, okay, there'll be a lot of disturbance. Got it? Or without knowing you, some amount has been, some data might be reduced. Okay, clear? Or some network issue in your area. So what you'll do, you will make a call, you will make call to customer. Got it? So you're going to make a call to a customer care. Is it? So when you dial to customer care number, what happens? The other side, okay, of the in the customer care center, one of the executive is going to receive your call, and then what you will do, you will tell your queries. Okay, you will tell your issues you're facing with that particular network to that particular representative. So that representative, what you will do, he will resolve your query. Clear with this? So I meant to say here, the system like banking system, what I used to tell earlier, now the system is a customer care center, or what I can say call center. Got it? So in this call center, there are two executives named Abel and Baker. Got it? There are two executives, Abel and Baker. So here, just one assumption is there. Abel is senior most. Okay, I mean Abel is an experienced one, and Baker assume it to be a new employee. Okay, so I mean Abel is an experienced one. He will answer everyone's query in lesser time. Got it? Means Abel is going to answer anyone's query in lesser compared to Baker. So in this problem, when Abel and Baker both are idle, means at present, okay, Abel and Baker both are idle, means whenever a call comes, okay, that call need to be answered very quickly. So Abel is going to answer that call. Clear? So if Abel is busy, then only Baker is going to answer that call. If Abel is busy, then only Baker is going to answer that call. Got it? And here, what I say here, this so what is an input? What is an input to call center problem? Input is nothing but call from the customers. You are not going to enter to the customer care. Just you're dialing a number on dialing a customer care number on your mobile. So your call to customer care center, call center is an input. Got it? So you're getting an output, right? That is response you're getting. Got it? For your query, you are going to get a response. That's an output to you. But what I said, I'm not concerned with output, what you are going to get, but I'm concerned with performance measurement. Got it? So in this case, okay, in this, I'm concerned with two performance measurement. How efficiently Abel is utilized. Got it? Means I may simulate for an entire day. I may simulate for 2 hours. assume that I may simulate for 2 hour duration. Means I'll run my simulation, call center simulation for 2 hours. In those 2 hours, I want to look at how efficiently able is utilized. Got it? That is one performance measurement. And in the same 2 hours, I need to see any number of calls may come to customer care. Got it? I want to determine on an average, okay, on an average, what may be the time spent for resolving the customer's query. Means how long the customer's call were in the system. Got it? You will dial a number, executive is going to answer, the duration of time is going to take to respond. Okay, that is the time spent by one customer. Got it? Time spent by one customer. Similarly, in two or any number of customers call may come. So I need to determine what was an average time spent for each customer. Clear? So the performance measurement I'm concerned here, or how efficiently able is utilized. Got it? And next, one more performance measurement is what is an average system time spent by each customer. Got it? So I mean, this is about the problem. So now solution is that I have a solution, I have a model. Got it? So my question to you guys, okay, for this call center problem, how efficiently able is utilized, and what is an average service time, system time for each customer? This is my question. So what you guys will do? In my question, I said for a duration of 2 hours. Got it? So what you guys will do? So one guy, what will do? He will generate some random input. Random input means that random input means inter-arrival time between calls. He will one guy will tell, sir, first call will come as soon as the customer care opens, that is at time 0. The second call will come at time 5. The third call time 5 minutes. Third call will come at time 15 minutes. Means one customer guy is going to generate his own random inputs for inter-arrival time for calls. Got it? So see, the other guy might give some other random input, right, for inter-arrival time between calls. Correct? I mean, one student will tell first call will come to customer care at time 0, second call at time 5 minutes, third call at 15 minutes, fourth call at 25 minutes, so and so. Second student will tell first call will come at time 3 minutes. Okay, second call will come at 9 minutes. Third call will come at 14 minutes, so and so. Got it? Similarly, two more students, let me assume 2 more students. They will generate their own random inputs. Clear? For inter-arrival time between calls to customer. Clear with this? So similarly, first student will assume, sir, for first call, service time might be 2 minutes. For the second call, service time might be 3 minutes. Fourth call, service time might be 1 minute. It depends on student. Second student will tell service time for first call may be 5 minutes. Service call for a second call be 3 minutes. Service time for third call be 2 minutes. So it depends. Means all 4 individuals taken their own random inputs. I repeat, all 4 individuals taken their own random inputs. Got it? Own random inputs, that is inter-arrival time between calls to customer care and service time for each call. Clear? So what I said, since random inputs are random, the output also random, right? So when all 4 students will run their simulation, got it? They will find Abel's utilization to be something, means the Abel's utilization of each 4 will be different. Got it? Clear? Abel's utilization of each 4 is different. Got it? So let me say for first student, okay, in his run, Abel's utilization, let it be 0.808. Just observe, look at a slide. For a first student, okay, let in his run, Abel's utilization be 0.808. And his average service time, let it be 3.74. Yeah. So for the second student, okay, let the Abel's utilization be 0.875 and service time be 4.5. Got it? Similarly, for third and fourth students, okay, Abel's utilization and service time you can see on this table. Got it? So, now what the first student is going to tell, sir, my according to me, Abel's utilization is 0.808 and average service system time is 3.74. So, should I consider first student's answer as a performance measurement of cost center problem? It need not be, because all four got different answers, right? So what we need to do here, see here, I said if theta, initially I said theta represents performance of a system, theta cap represents performance of system in one particular run. Got it? Theta for a whole in general. Got it? So see, let here for run one, for first run, okay, P1 cap is Abel's utilization. For second run, P2 cap is Abel's utilization. For third run, P3 cap is Abel's utilization. For fourth run, P4 cap is Abel's utilization. Similarly, service times, system times, W1 cap, W2 cap, W3 cap, W4 cap. Got it? So now what I need to do, my answer I can give, I can answer, you students can answer to me, sir. For example, say first student can answer to me, sir, Abel's utilization is 0.808, but with the standard error of some X. Got it? Second student can answer to me, sir, it's Abel's utilization is 0.875 with the standard error of something. Okay. Third student can answer to me, sir, Abel's utilization is 0.708 with standard error of something. Similarly, fourth student will answer. So first I need to how to determine the standard error. Got it? So to determine standard error, okay. Now what here? P1 cap, P2 cap, P3 cap, P4 cap you have. Got it? So determine its average. We call it's a mean. Got it? We call it a mean. Means sum all those four individuals utilization, Abel's utilizations. Okay, you sum 0.808 plus 0.875 plus 0.708 plus 0.842. You're going to get some value. Divided by 4. Okay, that is we call mean utilization of Abel. Got it? That's a mean. That's a mean. Okay. For example, we may, for example, let me pause for 1 second. So what I said, I need to sum all this four Abel's, all these four individuals Abel's utilization. Divided by 4, I'm going to get mean to be 0.80825, almost 0.808. Okay, but almost 0.808. Okay, means 0.80825. I'm going to get mean. So when first student answers to me, okay, so always going, sir, Abel's utilization is 0.808 with a standard error, that is difference between 0.808 and 0.80825. That is standard error of 0.00025. Got it? So similarly, second student may answer to me, sir, Abel's utilization is 0.875 with a standard error of 0.06675. Got it? So similar third student, what he will answer, sir, Abel's utilization is 0.708, okay, with an error of 0.10025. Error how we are going to get is nothing but difference between the mean utilization and individual's utilization. Got it? So in other way, this is about the standard error. In other way, what answer each can give is that, okay, see, if I run again for some more times, here I run that simulation for 4 times, right? Suppose I may run it for 5 more times. Okay, you run it for any times. Among all those runs, you find out least utilization value and max utilization value. Here, I can see that your least utilization of Abel was in third run, that is 0.708. Got it? And max utilization of Abel in second run, that is 0.875. Least is 0.708 and max is 0.875. So what you can tell, how you can answer, sir, Abel's utilization is in the interval 0.708 to 0.875. Clear? The confidence interval for Abel's utilization is between 0.708 and 0.875. Clear with this? So similarly for the system time also. So this thing what I explained to you, okay, see here, what I told, instead of performing a single run and concluding what the utilization I'm going to get in single run as an answer, it's not correct. We need to run for some number of times. Okay, so in the second point, P R cap, W R cap. R means run number. For first run it is 1, second run it is 2. Okay, clear. So I said look at 2 general questions. Those 2 general questions are nothing but standard error. Okay, and the confidence interval. See, first I said, right, estimation of true utilization. True utilization, P is something we call rho, right? A equals C of rho. That formula, okay? Look at the mouse pointer. Okay, this formula, rho equal E of rho or cap. Okay, so that means it's a mean value. Means all those 4 utilizations of Abel's are summed it and divided by 4. Got it? So what the mean I got? That is denoted by this P. Seems to be like P. Okay, rho. Got it? So that particular mean value we call point estimate. Okay, we call point estimate. And once I am mean, I can say, oh, what may be an error, right? For in each run, what may be the error that might have been occurred in utilization. So just now we had a discussion about Abel Baker call center problem. Okay. Now we'll take one more example, that is a single server queuing system. Got it? And the notation we know, right? We'll represent this as M bar G bar 1. Here. Now we will simulate it as a continuous time process. Okay, I'll tell you in this example, I'll simulate this single queuing server system as continuous time process. That I'll tell you, because in discrete systems like in previous example, okay, we know how to determine the mean, that is an average, right? You will sum all those and divide it by n. Got it? But if a system is continuous one, how to determine average? Okay, the question lies in determining average. This is just a difference in determining mean in case of discrete and in case of continuous. I'll tell you how to determine mean in case of continuous. Got it? So Now, let me say I have a single server queuing system. Got it? Let on an average, okay, 0.1 customer per time unit. Time unit may be a minute or an hour, whatever it be. In general, I'll call time unit. Okay. Let the average arrival rate, denoted as lambda, is zero point 0.1 per time unit. Means in one time unit, on an average, 0.1 customer is going to arrive. Got it? What I can say, in general, 0.1. To be more precise, I can say one customer will arrive for every 10 time units. Clear? One customer will arrive for every 10 time units. So per time unit, it's nothing but 0.1 customer. And let me say you are given an average service time. Okay, an average service time for each customer on an average. Let me say it's 9.5. 9.5. See, I repeat, we are given an average arrival rate lambda as 0.1 per time unit. Got it? And for each customer will may have its own service time, but on an average, the service time what has been given is 9.5. Got it? So average service time is denoted as E of S. E, I said, what is E? Like in a previous slide, okay? I mean, in previous slide, we have written E of P or cap, right? E means average. Got it? E means estimation average. Got it? So clear with this? Average arrival rate is lambda 0.1 per time unit. Average service time E of S is 9.5. And what is that sigma equal 1.75 means? It's a standard deviation. Got it? Means what is standard deviation? I said when I run for the one time, okay, I may get mean to be let me say mean service time. I might have found 9.4. Okay, sorry, I repeat. Here what I given is average service time. I have given 9.5, right? Okay, so next in next one I may get up to 9.25. Sorry, 9.5 minus 1.75. What is difference? 9.3 something. You just determine difference. Okay, 9.325. Got it? Or in the next one, you might get average service time to be 9.675. Means the standard deviation is that what may be how far or near the average service time may be with respect to estimated service time. Got it? So now you have average arrival rate, you have average service time. Clear? Now it's very easy to determine server utilization, right? We have that formula. Server utilization rho equals what? Lambda into E of S. With this, we will get server utilization as 0.95. It was 95%. Now, let me, in this system, let me concern with determining, okay? Let me concern with determining long run mean queue length. Okay, in this single server queuing system, now I'm concerned with one performance measurement, that is for the entire duration of simulation, what is the average queue length? Got it? For example, say banking system, okay, from morning 9:30 a.m. to evening 4:30 p.m. I will simulate, okay. And this entire duration of time, not for a particular time, for this entire duration of time, what was the average queue length? That is the objective here in this instance, in this context. Clear? So LQ of T in general, okay? In general, okay, let me say LQ of T, what it represents means in general the average queue length up to time T. Got it? up to time t, what was the average queue length? That is represented by LQ of t. Now, let me say, in this case, I will let me simulate, okay, for 5,000 time units. I repeat, let's consider that we are simulating for 5,000 time units. I mean, starting from time 0 until the clock ticks to 5,000. Okay, let me simulate. And let me observe this in entire 5,000 time units. What was the average queue length? Got it? So I will simulate for how long? 5,000 time units. That is starting from time 0 until clock stick to 5,000. In this entire 5,000 time units, I need to determine what was maximum, what was average queue length. Got it? So here, to make it simple, okay, to make it simple, what I'll do, I will divide this 5,000 time units into 5 batches. Got it? I divide this 5,000 time units into 5 batches. Means first 1,000 units, second 1,000 units, third 1,000 units, fourth 1,000 units, and fifth 1,000 units. Got it? To make simple, what I'll do, I will divide this entire 5,000 time units simulation into 5 batches of each 1,000 time units. And then in each of these 5 batches, okay, let me determine the average queue length. Got it? I repeat once again. Actually, I wanted to simulate for 5,000 time units from time 0 to time until clock ticks to 5,000. And I should have determined average queue length. That is LQ of 5,000. Okay. Got it? But to make simple what I said, I will divide this 5,000 time units into 5 batches, each of 1,000 time units. Then in each of these batches, I will determine what was the average queue length in each batch. I repeat, I will determine the average queue length in each batch. Once I have average queue length of each batch, okay, average queue length of each batch if I have, then each batch I can treat as discrete. Remember, listen, each batch sorry, don't get it's not discrete. So now suppose, okay, I have average queue length of each batch. Average queue length of each batch. Each batch I can treat it as discrete. So if you have average queue length of each batch, what you can do? You sum those average queue length of all 5 batches, divide by 5. If you sum the average queue length of all 5 batches and divide by 5, you get the average queue length of entire 5,000 time minutes duration. Got it? So I repeat, to make simple, to make continuous time process simple, what I told, I will divide 5,000 time units into 5 batches, each 1,000 time units. For each batch, I will determine average queue length. Got it? So once I have average queue length of each batch I can treat as a discrete. So if they are discrete, what I can do, I can sum the average queue length of those 5 batches and I can divide it by 5. I will get the average queue length for entire 5,000 time units duration. Okay, so this will I will look at next slide. Got it? See here. Just have a look. See, like in previous example, I said Abel Baker call center problem. I've run the simulation for 4 times, right? Has run the simulation model for Abel Baker call center problem 4 times. Clear? So in this table, what you can see is that I've run this single server queuing system, which is a continuous time process time. Okay, continuous time process 3 times. Each run we call a replication. Here I've used a terminology replication. Replication means each run. Got it? So now in the right side of this table, okay, last three columns, okay, column number numbered 1, 2, 3, it represents run, it represents replication. That means first run, second run, third run. Each run is for how long? See, each run, that is run 1, run 2, run 3, is for what duration? It's for 5,000 time units. Clear? Each run R1, R2, R3. It's for 5,000 time units duration. So what I said, this 5,000 time units duration, I have divided into 5 batches. That you can see in first column, 0 to 1000, 1000 to 2000, 2000 to 3000, 3000 to 4000, 4000 to 5000. Got it? Clear? So next here, so this batch J means what? Total in each run I have got 5 batches. Batch number 1, batch 2, batch 3, batch 4, batch 5. Got it? So look at the first row, okay, in the data field, okay, not in the data part, in the data part, first row of the data part. See, in the first run, okay, first row, that is in the batch 0 to 1000, okay, y11 entry y1, y1, okay, that is first one, index 1 is run 1, replication 1. J represents which batch. Here J represents which batch. Got it? J represents the batch number. Got it? So y11, you can see it as 3.61. Means y11 equals 3.61. It means average queue length, okay, in batch 1. Got it? Next, y12 equals 3.21. It means average queue length in batch 2. That is for the time duration 1000 to 2000. y13 equals 2.18. Got it? 2.18. It is the average queue length in batch 3. y14 equals 6.92 is the average queue length in batch 4. y15 equals 2.82 is the average queue length in which batch 5. Okay, so now for all this 5 batches, okay, I have the average queue length. Got it? So what I said, sum all this 5 divided by 5. Sum all this by average queue lengths divided by 5, you will get the average queue length for entire 5,000 time units duration. Got it? Clear? So that will represent as y1 cap. See, y1 on the top of y I have written dash, right? That is, let me call y1 bar. Okay, y1 bar equals 3.75 means, listen, I'll tell you, y1 bar equals 3.75 means it was the average queue length of customer for the entire time duration of 5,000 time units in first run. Got it? Similarly, for second run and third run, the average queue length is y2 bar equals 15.56 and y3 bar equals 13.6. So clear? Got it? But clear with this? So like in Abel-Baker problem, I've run for 4 times, but here I've run for 3 times. Got it? So next, y1 bar, y2 bar, y3 bar. So exact, what I can say, exact mean estimate. Estimate, the estimate is nothing but average of all these 3, right? Means y1 bar plus y2 bar plus y3 bar, then divide by 3. Got it? So now the question is that, is there some difference, okay? How to determine the average queue length of each batch? Average queue length of each batch. Got it? The question here is determining average queue length of each batch. And I said it's a continuous system, right? Yeah. Now, I said each batch is a continuous. So each batch is continuous means how to determine the average. Here, it's not like summing all the values dividing by n. Here you need to make use of integration. I repeat, be cautious, listen carefully. Since it's a continuous system, determining mean or average is entirely different. Here we need to make use of an integration with lower limit to upper limit. Got it? So that I show you in the next slide. Now clear with this, right? So each run is for 5,000 time units. It's a continuous time process divided into 5 batches, of which 1,000 units, 1,000 time units. We have determined average for each batch. Each batch then I can consider as a discrete, then I can determine mean for each batch, mean of all batches. Got it? So now, see here, for example, let me say batch number 1, okay? So batch number 1, okay, just have a look. Batch number 1, what was time duration? 1,000 time. Starting time for batch 1 is 0, right? And end time is 1,000. Clear? Start time of batch 1 is 0, and the end time of batch 1 is 1,000. Clear? So in general, okay, J represents batch number. Okay, so the average number of customers in the queue from time 7 for batch 1, J is 1. 1 minus 1, 0 into 1,000, 0. 0 to 1 into 1,000, 0 to 1,000. Okay, clear? 0 to 1,000. Got it? For batch 1, start time is 0, end time is 1,000. When I say batch 2, J is 2, start time is what? 1,000, right? 2 minus 1, 1 into 1,000, 1,000. 2, 2 into 1,000, 2,000. Got it? For batch 3, 2,000 to 3,000. 3 minus 1, that is 2 into 1,000, 2,000. 2, 3 into 1,000, 3,000. Clear? So I said that to determine mean, I need to make use of integration. Got it? I need to make use of integration. So LQ of T, okay, LQ of T, what I said is the average Q length, okay, for that time up to time T. Got it? So the lower limit J minus 1 into 1,000, upper limit is J into 1,000. For this integration, I need to divide by 1,000. Got it? I'll get average, what is that? Average length of customers in queue of each batch. Clear? The last two figures represents that is average queue length of first batch and second batch. Now, what I said, I run it for 3 times, right? There was 3 replications. Okay, one numbered 1, 2, 3. So now what I said, y1 bar, sorry, y1 bar. See here, last row, y1 bar, y2 bar, y3 bar. What are they? They are the mean estimated. They are the mean. They are the estimated average Q length, estimated Q length in all 3 replications. Estimated Q length of all 3 replications. Now what I said, you divide. So, I repeat, y1 bar, y2 bar, y3 bar. I should not say estimated. Okay, sorry. Y1 bar, y2 bar, y3 bar are the average Q lengths of 3 replications. Got it? I repeat, y1 bar, y2 bar, y3 bar are the average Q length of customers in 3 replications. To get estimated Q length, what I should do to get estimated Q length? I should sum this y1 bar, y2 bar, y3 bar, and I should divide by 3. Clear? So that is shown here. Got it? That's not shown here. Sorry. This is see here, don't get this slide is entirely different. That is estimated Q length. Okay, y1 bar here in this slide I'm showing computing y1 bar, computing y1 bar, computing y2 bar, computing y3 bar. Okay, so how to look at the third column, that is third column last row, that is y1 bar. How y1 bar is computed? Y1 bar is computed as y1 bar is computed by adding 3.61, 3.21, 2.18, 6.92, 2.82 and dividing that by 5. Yeah, so that here this slide shows computing the average of entire one replication. Computing the average of entire one replication for the entire time duration of 5000 time minutes. Clear? Clear with this? And there is we'll wind up this, okay, with some highlights, some points we have noted about replications. Okay, so as the second point, what it says, there is an inherent variability in stochastic simulation, both within a single replication and across different replications. Means there's a variability within a replication, or there may be a variability among the replications. I'll tell you, it's very simple. What actually inherent variability means? Got it? So first, within a single replication, got it? Just observe within. Let me take here. I told you about replication 3. The average Q length over the batching intervals varies from low of as low as 7.67 to as high as 20.36. Got it? See here. Just observe last column. See, there are 5 batches. In each 5 batches, what I found, there's a variability of average Q length of all 5 batches. Okay, and that variability was as low as 7.67. Is it the variability? Okay, just observe last column. Got it? Average Q length varies from batch to batch within the same replication, that is with as low as 7.67 to as high as 20.36. Got it? This is within replication. There's an inherent variability. Now among replications, okay, for example, let me consider third batch of all replications. Got it? Let me consider third batch of all the replication. See, in third batch of all the replications, okay, that is y13, y23, y33, I find the average Q length varies. Got it? So this is inherent variability. Inherent variability within a replication or inherent variability across replication. Got it? Clear with this? So I think all of you got to know about estimating the performance measurement. Clear? Clear with this? So what actually stochastic means? Randomness. Since inputs are random, output also random. See, we have seen in each run, okay, in each replication, the first replication average Q length is 3.75. In second replication, average Q length is 15.56. In third replication, average Q length is 13.66. So this difference in output is because of difference in input. So this is because stochastic nature. Got it? So this is about today's session. Okay. Thank you for listening.